All right, good afternoon, everyone. Thank you for attending today's webinar, How to Eliminate Mechanical, Vibrational Loosening, Clampload, and Corrosion Failures in Your Products, brought to you by Henkel and Design World magazine. My name is Paul Heaney, and I'm the Editorial Director for Design World. A little background on me. I have a mechanical engineering degree from Georgia Tech, and I've been covering manufacturing and engineering for almost 15 years now. I'm pleased to be your moderator here today. I'd like to take this opportunity to thank our presenter for being here today and to introduce him. Douglas Carbeau is the North American Director of Technology Management for Anaerobic Products for Henkel. Doug works in Rocky Hill, Connecticut at the company's North American headquarters. He has a BS in chemistry from the University of Hartford and an MBA from the Loyola College of Baltimore. Now, during his 33-year career at Henkel, he's worked with the Loctite brand products in R&D, technical service, and sales and marketing. In his role as Anaerobic Technology Manager, he's responsible for thread locking, thread sealing, retaining, and gasketing products. Now, just a couple of housekeeping details before we get started. If you wish to tweet about this webinar anytime during or after, and I hope you will, you can use the hashtag DWWebinar, which is all one word. We will have a Q&A session after the presentation, and with the Q&A today, along with Doug, we're pleased to have Robert Dunkel, Technical Service Manager, who will also join in at the end to help answer any of your questions. So please go ahead and submit your questions as you think of them, and then we will ask as many of them as we can after all the presenters are finished. The questions can be asked using the GoToWebinar dialog box, which you should see on your screen there. And now, without any further ado, on to our presenter. I will hand the mic over to Doug. Doug.
All right. Well, thank you very much, Paul. And I want to thank Design World for hosting this webinar and everyone that's joined in for participation. So let me get started with this. I know people's time is valuable, and I would like to be able to get through the presentation, talk about increasing reliability for threaded fasteners, and then still have time so that people can ask their questions. All right. Oh, there's a little bit of a lag here on the. Okay, so we'll start out with hopefully why people are here. Everybody on the engineering side, of course, is interested in working on exciting projects, and I picked this particular example over here of a drone, figuring this is one of those advanced technology projects that's just a lot of fun to work on. Everybody wants to be successful with something like that. The last thing they want to be is somebody who's responsible for that little tagline at the bottom, which was of a failure. And in this seminar, what we're going to be talking about is how to improve the reliability of threaded fasteners. And we're going to talk about three elements of that. The first is a fastener is successful when it delivers the clamp load that it's designed for. The second is that that fastener needs to maintain that clamp load over the service life of the vehicle. And then the last is that oftentimes service at some point is required, and you need to be able to get that fastener back apart again. So it's another critical element of fastener design. We're going to cover all three of these during the course of this session. All right. So what we want to go with is, if you took a look at that popular mechanics article that I started with on the death of a drone, you notice that it talked about a loose screw down to $73 million aircraft, but it doesn't say why did that fastener loosen. And that's really the key here. What we want to go into is the root cause of what causes failure on a fastener. And I think once if you understand the root causes, makes it that much easier to take a look and evaluate the options you have for addressing the specifics of your situation. Oftentimes, if it says it just was a loosening, that doesn't tell you enough. When you do get a failure, it could be that you're looking at the results of the failure, which is either a broken or yielded fastener. And at that point, that still hasn't told you enough about what was going on in the situation. You need to dig a little bit deeper in there, and you really need to understand, again, going back to those big three we talked about, what was the problem? Was it didn't have enough clamp load to start with, or did it lose that clamp load somewhere along the line and then fail? So in the course of this, we really want to take it down one more notch, and we're going to start out with maybe a fundamental understanding of the mechanics of a fastener and how it operates. Okay, so very simply, on bolted joint mechanics, if you were to take a fastener and unwind the thread on the fastener, and here I have two examples of a coarse and a fine thread, where we've essentially just stripped out the thread, and you can see that it is really nothing more than just a simple ramp. And on a coarse thread, which would typically have 16 threads per inch, this ramp is about a 3-degree ramp. And the functioning of the fastener is very simple, very fundamental, and that is you are taking and driving the threads of the nut along this ramp. And as you drive it along the ramp, you are reaching the point where the fastener is secure, and then as you further move the nut along the ramp, you actually start to stretch the bolt. And when you start stretching the bolt, that is what creates the clamp load. That's what you're paying for when you have the fastener. And that's what provides the functional benefit of the fastener. A little different representation of it is in this next slide, where you can see that tightening that we've done on the fastener is actually stretching the bolt. And here we're using a spring kind of as a metaphor for that fastener, where once you've applied the specified torque to the fastener, you've stretched the bolt, and you now have a spring force that's holding your surfaces together. And if we take this lower nut here, I'm going to go to an exploded view of it. And what I'm kind of illustrating here is what I chose this photo for is very representative of what you've got. You've got a gap that's required in the thread root, and you need that obviously so that you can move the nut over the bolt and tighten it up. These gaps, though, this comes to the root cause of the performance that you get out of a fastener, and also how you can get a failure out of a fastener. This surface right here where the thread roots intersect is where you are driving the two ramps over each other. It's also where you're generating a lot of the friction, and it's this friction generated here which actually holds that fastener in position. Now there are other places where the friction is holding it together, but this is one key area. We're going to come back to this a little bit later. This open space, which you can see with the fluorescent material, and this is the helical space that occurs between the nut and bolt. This is where you can get some movement under various conditions, and this can cause loosening, or it's a root of how loosening occurs once you get movement in that area. And that area is also a helical path where you can get leakage, and we talked about a third type of failure, and that is corrosion, where you can't get the fastener to be disassembled. That occurs in this area. So we're going to revisit this area as we move through this presentation. All right, so vibration loosening. Don't need to say an awful lot on this particular slide because I think most everybody's pretty familiar with the fact that when you get either thermal transitions, which cause expansion and contraction of fasteners, or you can see on the right-hand side any type of vibratory loads, you can get a shifting between the nut and the fastener. And as soon as you get any type of micro movement caused by thermal or vibration, that's when you can get a loosening on this fastener, and that will reduce your clamp load and can result in failure. This particular picture that we have right here, please keep this in mind. We're going to get onto a test rig a little bit later, and this is the basis of the test rig. It has two plates that are bolted together. It's called a Juncker machine. A side sliding action is incurred between these plates, and it's a very effective test of different types of thread fastening devices to see how effective they are. So returning to how do you get loosening, again, we started out the presentation by saying that if you unwound the thread from a fastener and you drive the two forces, the two faces, the nut and the bolt, over each other, you end up with a stretching of the bolt, and you get a lot of friction, particularly on the thread roots. The clamp force is holding this together, and if you get any type of movement between the surfaces, you will actually lead to an unloading of these threads. And typically when you take and tighten up a fastener, and I'll use a half-inch fastener as an example, when you've tightened a half-inch fastener to its recommended torque, you're generating on the order of 5,000 to 12,000 pounds of clamp force on that. So that's holding these two surfaces together and obviously your fastener together. But if you go to disassemble a nut and a bolt, it typically takes about 70% of your tightening torque to start a fastener to loosen again. So, and again, it makes sense when you think about the fact that when you're tightening a nut and a bolt together, you're driving the surfaces up a ramp. Once you try to reverse that and move it back down again, it's actually much easier to move it back down the ramp. That's why it only takes 70% of your tightening to get a loosening. So that comes into play when you have vibration loosening. It doesn't take much to start that unwinding and relaxation of your clamp force. So let's go to how do we typically prevent loosening then? The traditional method, and there are many, many out there in the marketplace, is a mechanical approach. And one thing that's pretty typical with a mechanical approach is that they rely on creating additional friction to prevent loosening. And I'm going to show a couple of examples shortly of the different types of standard mechanical devices that are used to prevent loosening. But when you take a look at how they function, just keep in mind when we were looking at the cross-section of a threaded fastener, you have a gap between the two surfaces. Typically, they're not addressing that gap. They're not going to the root cause where you can get side movement to prevent loosening. They're taking a totally different approach, which is to increase the friction to prevent loosening. And when you are taking a look at mechanical, it also typically requires a customized solution. So for each size fastener and type of plating and type of environment, you will need a customized solution to meet the requirements. All right, so this is just a representation of a couple of standard, tried and true. The spring washer and the star washer both take a similar approach. In the case of the spring washer, the concept is that it adds some additional force required to compress that spring washer. And as a rule, that small amount, which can be just a couple of pounds to depress the spring washer, is not enough to prevent loosening. I know in some NASA studies that they did of fasteners, they found this to be really ineffective. It's more of a bearing surface than a thread locking device. The star washer and some of these other serrated methods like the flanged face take the same approach of trying to increase the friction to prevent the backwards motion. We have the castellated nut here, the tab washer, wired nuts like used in aerospace. Another common approach where in this case they're actually using a mechanical device to prevent the loosening of the fastener. So it's a mechanical device. The nylon insert takes a different approach. Here they're actually using a material to fill in the empty space on the threads. And it's a interesting approach, but it doesn't fill the load-bearing threads. The nylon insert is typically a non-load-bearing threads. And in many cases, its most effective use is just to prevent the nut from coming completely loose. Lock nut, just, well, if one nut's good, let's try two. And then with the ramp washer, again, increase the friction. This is a pretty effective technique here, where if you look at this very closely, you actually have to raise these two surfaces over each other on the ramp to achieve a disassembly. So this is pretty effective. And again, the mechanical approach, there's a lot of creativity that goes into this. Okay, so let's get to some testing, and we actually have a couple of different tests we're going to review now. This first one is a Yonkers transverse shock tester. I apologize, we had a video, but it was too large to play effectively, so this is just a picture of the machine. It applies a cyclical load to two metal plates, and if you recall a couple of slides back, I had a very simple picture of a bolt that was secured between two metal plates, and in this process, you actually put a mechanical device or your locking device on the fastener, you run it through the two plates, you tighten it to the specified torque, you turn on the transverse shock tester, and it essentially hammers the two plates and moves them relative to each other, creates side sliding, and it's a very effective method to very quickly generate data on relative performance of different locking devices. And there certainly is a difference. Some are much more effective than others. So in this picture, these are the results. And I'll start at the bottom with the unsecured fastener. If you've just taken and put a nut and a bolt together without any type of locking device on it at all, you tighten it up to the 100% clamp load. You start the machine and start running the cycle, as you can see, within 100 seconds. Because of the thousands of cycles it runs through, you very quickly will lose your clamp load on just a standard nut and bolt without any type of locking device at all. Then we talked about the split ring washer, and with this it adds some load to the nut and bolt, and you can see this is not far behind it. And the tooth lock washer, a little more effective because it does increase the frictional force between the faces. The elastic stop nut, again, this is something that you can see actually does give you some residual, but this critical element is you've lost your clamp load rather quickly. It's when you get into the severe ribbing that we had on like the sawtooth flange nut that you can see that that increase in the friction is probably the most effective way of mechanical devices to prevent the loosening. It does actually retain a fair amount of the clamp load. So those are traditional. Just waiting for this slide to refresh. Oh, there we go. Sorry about that. Non-traditional solution then. So the other approach that we wanted to introduce is actually addressing the approach with a non-mechanical and going in with a chemical solution. In this case, it's a liquid that's applied to the fastener. When the two parts are assembled, that liquid will cure and completely fill the thread root. The key method that this uses is it approaches the problem with from a different angle. Instead of trying to increase the friction, it actually takes and fills the inner space that occurs between the nut and the bolt. It cures into a hard thermoset plastic in between the threads. And in this case, you actually have two counteracting forces. One is it prevents the relative movement of the nut and bolt by preventing the relative motion of the threads side to side when you have all that impact going on. It actually prevents the side sliding and therefore the loosening. And the second effect that you get is this is an adhesive material. So it actually does bond to the lateral surfaces of the threads and further increase the frictional force of trying to disassemble the fastener. And so it's a totally different approach, and as in a different approach, it addresses the loosening at the root. So taking that same test that we just referred to, I've now added in the chemical thread locker, which has a very effective performance curve of maintaining the clamp load of the fastener. And the last element that I wanted to address is that it's always important to keep in mind cost and performance. And mechanical devices do vary in their performance, some being more effective than others. But when it comes down to cost and performance, you have a one-sized chemical thread locker that can treat a variety of sizes of fasteners versus a multitude of different styles that would be required to be kept in inventory and typically have a much higher acquisition cost. And so you can really get a very high performance, low cost solution with a chemical thread locker. So it's reliability and performance. But the performance comes because of the fact that it operates on a different methodology. So we talked about maintaining clamp load, and we said there were three areas of concern. One was maintaining the clamp load that you have on the fastener. We've covered that. Second was allowing the fastener to be disassembled. And this one I'll be very brief on. The liquid thread locker fills the threads, then it cures. So this is a partially disassembled corroded fastener, the key being that because the interface between the nut and the bolt have been sealed by that liquid plastic, you do not get any leakage through there, and in this case you don't get any corrosion. And so that does allow you to disassemble it when it becomes time for service. Now you do get heavy corrosion along the rest of the threads. The chemical thread locker does not prevent that, but what you will find is if you do not have corrosion between the two surfaces, you can disassemble a fastener. This bolt will run over the corroded sections of the threads. It's typically the issue of getting it started where you have the problem. And I just chose one sample here, an example, which is where there was a failure. And again, going back to the original premise of this, oftentimes when people are doing root cause analysis, they only take it to a certain level of what was the failure mode without getting all the way down to the lowest level. And in this case, this was a packing nut or a gland on a pump, and the problem that was occurred was the shaft corroded, and when they disassembled it, the most obvious reason that it failed was that it had not been adjusted to allow a weepage of fluid through there as it's designed to. And so you could say there was a failure of the packing. But the reality of the situation, let me get that next, sorry, was that the reason it wasn't adjusted so that you had a weepage and you didn't get the shaft failure was because the fasteners had actually corroded. So the mechanic who went in to do the maintenance was unable to make the proper adjustment, and therefore, since things weren't kept adjusted, you ultimately had a failure in that shaft, and then they had to be disassembled and taken apart. So for corrosion, the chemical thread lockers, again, go to the root cause. It's a different approach than mechanical, and that is it actually fills this thread root. It seals this helical thread path. This is a very tough thermoset plastic that fills this, very temperature resistant, solvent resistant, and it prevents corrosion from occurring so that when you go to disassemble it, you will not have lost any of your, or you will be able to disassemble it with a normal wrench. All right, so we've talked about two of the three. The last element we were going to talk about as far as fastener failure, so we've talked about achieving the clamp load, or I should say maintaining the clamp load with vibration. The second was the corrosion, which was preventing that in the first place, the root cause. And now the third we want to talk about is just achieving the clamp load the fastener was designed for. And many variables go into the proper clamp load that's designed for a fastener, one of them being the grade of the fastener, what's it designed to handle for clamp load. And let me just build the slide out to the 3 so you can see them all at one time. Achieving the proper clamp load on a fastener. So just, again, to give you an idea, if you have a half-inch fastener and it's a grade 2, that should be generating approximately 6,000 pounds on clamp load for a grade 2. For a grade 5, it should be able to achieve about 9,000 pounds of clamp load, and for a grade 8, about 13,000. And that only will work if you properly tighten the fastener. And there's a variety of methods that are out there for tightening a fastener and measuring the clamp load. Putting a micrometer and actually measuring the amount of stretch on the bolt is obviously a very precise way to measure clamp load, but it's typically only used in highly critical applications. There are also certain types of bolts out there that are designed to yield when they achieve their clamp load. These, again, are more of a specialty or niche type of solution. In most cases, it's using a torque wrench that's used for determining or applying the appropriate clamp load. And so what we want to go into is 2 lab studies that we did just to show the effects of different variables on the generation of clamp load. So this slide here says only a small amount of energy from a torque wrench goes into actually creating the clamp load. 85% of the force put on a torque wrench is consumed in overcoming friction. That friction occurs along the threads and along this face. Those are the major areas. So only 10 to 15% of the force that is applied with a torque wrench actually goes into stretching the bolt to achieve your clamp load. So understanding that, I think the next couple of demonstrations that we do with of laboratory data that we review, it'll make it easier to understand how small changes in lubricity can have a significant impact in the clamp load that's achieved. Here we've got a couple of the factors listed that come into the amount of clamp force that you can generate with a torque wrench. So the first test that we did was actually very straightforward. What we wanted to do is get a selection of fasteners from various manufacturers and test to see how much variation there was in clamp load just assembling them using torque specs straight out of the manual for these fasteners. We chose for this particular test zinc-plated fasteners, very common, and we mentioned the fact that only 10 to 15% of the force that you apply to a torque wrench actually creates the clamp load itself. The rest goes into friction. So we did want to note that in this case, there was no oil film used on this type of fastener because, because of the zinc coating that prevents the rust. There's no oil, so it's a non-lubricated fastener. All right. So in this case, we were using 5/8 coarse thread, grade 5, and the recommended torque is 112 foot-pounds. This is the test system that we used. It's a system where you can apply the torque and then directly measure the pressure and from that generate the clamp load that's being achieved with the fastener. So it's a direct measurement. And if you have questions on this, we can take that at the end. This is just a schematic, very simple. Pressure gauge. The force is being generated in this hydraulic fluid as you tighten the fastener, and then you can get a direct read on the pressure gauge. So 5 fasteners, or 5 different manufacturers. We applied the recommended torque load to them, and you can see the range of the clamp load that was measured on the fasteners ranged from about 6,000 to a bit over 10,000. So about a 20% range. So then in the next we repeat that exact same test, but in this case these were the dry results with no material applied to the fastener. These are the same bolts, well, same manufacturer's bolts. They were new bolts that were reassembled using a liquid thread locker on them. And the observation that we had is that we had much less scatter in the clamp load. In this case, the liquid thread locker is actually acting a bit as a lubricant, and it is giving a more consistent amount of end clamp load, which is what you're paying for the fastener for. So it's giving less scatter, more consistency, and again, more reliability on in this test. Okay, so in this case, it's strictly generating the clamp force that we're evaluating. This just shows, obviously you still get a little bit of scatter, but the main being it's a tighter grouping. Okay, so we're often asked on our technical lines about friction factors or K factors, and actually on our website we do have some information about K factors. There's a large number of variables that go into it. A lot of it has to do with different types of elements that affect friction. I guess the key thing that we wanted to say is it's actually experimentally determined for an entire system, not just for one component in the system. So for you to have a valid figure, you really need to evaluate the entire fastener system rather than just one component of it. And the reason, so let's actually go into a test then that we did. All right, so in this case here, we have a range of chemical and mechanical systems. The exact same test system that we did. Again, it was the 5/8 inch bolts. And what we're shooting for here is to have this is the K factors that was measured for these specific systems then. And what we were looking for in this test was just how does it compare to the K factor we would have if it was an oiled fastener. So you can see not much of a difference between dry and oiled. These were a variety of different liquid thread lockers that were tested, this one being an anti-seize, and this being the ramp washers that we showed in one of the earlier slides for a mechanical solution. We just wanted to have a comparison in here because, again, what we're trying to show in this test was if you take and vary the system, what effect does it have on the K factor that you have? So this first slide is for these specific systems, what did we measure for a K factor? You can see the range of values going from over 0.35 down for anti-seize, which was the low of about a 0.13. And then this is how that K factor then translates into, we've applied a recommended torque for oiled fastener to these 5/8 fasteners, and you can see how that variation in K factor translates into a variation in the clamp load. And again, when you purchase a fastener, you're purchasing it for the clamp load. You get a fair amount of consistency, but when you have a system like anti-seize, which dramatically reduces the K factor, increases, to make that clear, as it says right here, higher K factor, lower lubricity. So this would be, on the anti-seize, it was a low K factor. It acts as a lubricant. More of the force that you're applying in the torque wrench is going to generating clamp load. So you get your highest clamp load with an anti-seize. If you take and are using that same unadjusted torque value, you're generating much lower clamp load with the mechanical fastener. And this would be the concern that from the start you have not achieved your design clamp load for the system. So it is important to make sure that your torque specs are set so that they accommodate the thread locking system that you are using, whether it's mechanical or liquid. And this just summarizes for that ramp system. So again, key being, if you are changing the type of thread locking system that you're using on a device, just make sure you've similarly adjusted the torque that you're going to apply so that you achieve the clamp load, always keeping in mind that the objective of a fastener system is to get the design clamp load that you have for that system. So again, those two studies that we did were showing that only about 10 to 15% of the torque value is going to generate your clamp load. So if you are going to be changing your friction or K factor for the system by the thread locking system that you select, you do need to probably adjust the amount of torque that you're going to put in. In the testing that we were doing, we were finding that using a liquid thread locking does seem to bring more consistency to the system, that the applied torque is going to generating clamp load, and you get more consistency across different manufacturers' fasteners, as well as you end up with a more consistent clamp load as a as-received fastener, which was shown in that second study. And then, as we said earlier, once you've cured the thread locker, the liquid thread locker, then you also get the additional benefits of very effective at preventing vibration loosening, as well as preventing corrosion, so you can disassemble the fastener. So we'll move to the summary here, and then we'll go into some improvements in the products. If you have to maintain the proper clamp load over the life, so we talked about vibration loosening and mechanical and chemical methods of achieving that. If you don't have your clamp load to start with, lubricity is a key factor in generating your clamp load, because so much of the clamp load is dependent upon overcoming the friction of the assembly. And then preventing corrosion will improve the reliability of your system. All right, so that's the summary of the traditional and non-traditional, and the three root causes of fastener performance and reliability. Root cause, if you take it down to the lowest level, you really want to design a system to make it most reliable. You can do that by preventing the micro movement that occurs between the nut and the bolt, and then preventing corrosion so you can disassemble it and service the system at the end of its life. All right, so I've got about 3 or 4 minutes before we go over to the question and answer. I'll just wrap up with a couple of improvements on chemical thread locking. The systems have been around for about 40, 50 years. One thing, just making sure that people are aware they are designed for various strengths. If you have, in 80% of the cases, it's recommended to use a medium strength thread locker, which are color-coded blue, so that you can service the fastener. There are the high strength red products, which are designed for permanent assembly. But when we do say permanent, you can use heat to soften the thermoset plastic and then still disassemble the system. It's just that in most situations, this red will prevent fasteners from being disassembled, and you use them selectively like a stud into a housing. And then we also do have low-strength fasteners, which are typically designed for either screw applications, where you may have a long thread engagement and a relatively low-strength fastener, and that would be where you would use a low-strength product. A recent improvement in the chemistry has been where Earlier generations of the liquid thread lockers required a primer when you were using them on a stainless or plated surface, and that was simply because of the cure chemistry of the product. When the materials are applied to two metal surfaces and the surfaces are combined, that excludes the oxygen that allows the thread locker to cure. But in addition to the exclusion of oxygen, you also require metal ions. And the older systems required them to be added to the system by the use of a primer or an accelerator sprayed onto a stainless steel or plated surface. The latest generations of the thread lockers is shown here. These would be older generations. This would be the newer, where even on a stainless steel surface, which does not have any free metallic ions, the activator system within the adhesive is able to cure and cure relatively quickly without any secondary operation. The main benefit of this is that in a production environment, you have a more robust system that can tolerate different surfaces without having to have a secondary operation. The second table on here is that the other improvement that's been made in the chemistry is for oil tolerance, and typically on a number of fasteners, either where they've been in service or when they're received new from the manufacturer, you can have either cutting oils or machine lubricants on the fastener. And it used to be that with older thread locking materials, it was always recommended to clean the fasteners. The newer generation actually will work regardless of having an oil film on the fastener. So again, eliminates one more preparation step, one more processing step, makes it a much more production friendly and, more importantly, a more reliable and robust thread locking solution. Other improvements have actually been in form. So for since the introduction of these materials, they've always been liquids, but over the last 10 years or so, additional forms have been developed and introduced in the marketplace, products that are actually in a gel or stick form so that you don't get any migration. And the latest that came out a couple years ago was actually as a tape, where this is actually a dry film, applied a couple of wraps, and when the nut and bolt are assembled, the grinding action actually releases the liquid and causes the cure to occur. The film can actually be applied up to 30 days prior to assembly, so you can actually use this a bit as a pre-applied system as well. And processing, another important aspect of a system. It's always possible to go to either a semi-automatic or an automatic system for high production applications. This allows you to have better control over the amount. But I would say most customers will probably get the most benefit out of this applicator, which is a peristaltic hand pump. This screws directly onto the bottle. This trigger has a fastener or a screw in it, which you adjust in and out, and that allows you to control how much material is applied by the operator onto the fastener. This simple device is probably the most effective because many applications are being done manually, and this is a reusable applicator that allows the engineer to have better control over how much material is being applied in a production environment. Over applying the material doesn't do you any benefit because the excess product outside of the joint does not cure, it doesn't fill the threads, it doesn't prevent the corrosion. It's only the material that's applied right on the threads where the two surfaces join that really provide you all the value that you get out of the system. So with this type of applicator, you have a very simple method of ensuring consistent application of product to the joint and getting the maximum benefit out of the material. And the last system is also a thread locker. This is a pre-applied. In this case, it's typically not done in the plant environment. The thread locker is usually applied by an outside vendor and come into the plant with the product already pre-applied, ready for use, and they have a multi-year shelf life. Okay, so I want to leave time for questions. I'll just show some additional specialized products that are available for specialized conditions. We have products that are rated up to 650 degrees Fahrenheit. We have materials that have been introduced for improved health and safety. I know these are very popular in Europe and have some popularity here, where they are materials that have no skin sensitivity, also no Prop 61 warnings because of the chemicals that are used for making them. Other products that are designed specifically for the food industry, where these are designed with materials that are on the Federal Register. Low halogen, high purity products designed for the power gen industry, the nuclear power gen. And then some materials are liquid thread lockers tend to be a liquid thermoset plastic. So we have special grades that are designed for using on plastic fasteners without causing any stress cracking. And then a full range of materials that meet military specifications as well as CSA and UL and other types of specialized specifications. Okay, and with that, maybe I can open up the floor to questions and bring Rob Dunkel on the line with us as well.
Thank you. That's great information, Doug. We really appreciate it. So as Doug said, we'll use the remaining time for questions. And then along with Doug, we're pleased to have Rob Dunkel join in to help answer the questions. We already have some questions that have been coming in, but it is not too late to send yours in. Just use that dialog box on your GoToWebinar screen. All right, first question, gentlemen. We have a viewer who is concerned about disassembly. What is the effect of using high-strength red products on disassembly?
Rob,
yeah, it's Robert Dunkel. I'll just respond to that. Yeah, when you use a red high-strength product, it can cause some difficulty disassembling, but it's often dependent on fastener size. For example, if you're using it on like a 3/4 inch and up bolt, you can use a high-strength thread locker, and it comes apart with the same tool you put it together. But when you deal with fasteners that are smaller than a 1/2 inch, that's where really the size or the strength recommendation is more critical. And really the key is to actually use a removable grade from the start, and then there's no issues with removability.
Okay. Another question, primerless was described in your chemical thread locking advances section. Does this mean that primers are no longer required?
Yeah, it's Rob Dunkel. I'll tackle that one again. Yeah, the newer technologies we have, we recognize there's more and more non-corrosive metals like stainless steel and even aluminum being used for bolts, or you're bolting into an aluminum part. The products initially required contact with a metal that would corrode to provide half of the cure system for how our products worked. The newer products we actually have are designed to work on stainless or aluminum without the use of a primer, which is helpful because even the primers themselves, because of environmental regulations in some facilities, have been banned because they don't want materials that you might have. The primers can introduce additional concerns, and then there's the possibility of someone forgetting to use them. So the newer grades that Doug talked about are designed for on stainless or aluminum. You can just use them as a one-part system.
Okay. How sensitive is chemical thread locker performance to different application variabilities?
Again, with our product tends to be very robust, which means you don't. The newer products were designed to be oil tolerant, and that's part of our criteria for developing products now. That we recognize there may be residual oils left on a surface. Again, because the cleaners that were used in the past have been banned for other regulations. The surfaces we're presented with are not as clean, so we are designed to cut through a light oil film and still cure effectively. Obviously, the cleaner, the better, but when the products were out in the 50s and 60s, you had to have a degreased surface to get them to work properly. These days, that is no longer a requirement.
Okay. Another question just came in. Does the K factor apply only at the time of assembly?
Yeah, that's a fair question on that. The K factor is one of the more misunderstood parts of bolting, in that it's a collection of every variable that changes in a system. But the questioner is correct in that it only is assembly. When you put it together and torque it down, how much torque you apply relates to how much clamp load. But once it's together, you're not actually concerned with it anymore.
Okay. What type of thread locker would you recommend for a high temperature application?
We have two different products. It's probably best to consult our catalogs for it. Most of our products are good to, the older generations were good to about 300 Fahrenheit. The upgraded ones we've brought out are good to 360 F. Most products that, or the most common application in machines normally have oil, and you don't typically have oil over those temperatures, so usually you can just use the regular grade. We have some grades that are good to 450, and we have some grades that are good to 650. It all depends on the application you're doing it.
Okay. Next question, how do you reassemble with a thread locker? Do you need to clean out the internal thread of the nut, and if so, how would you do that?
Yeah, that's a really good question. We get a lot in terms of how do you reassemble. With our products, typically what will happen is anything loose should be removed. So if you have the bolt, it's easier. You can just brush it with a wire brush. When you have the nut, obviously there's no easy way of getting inside. We normally just say use it as is. Make sure you clean off the bolt itself. And our product will stick to itself. And so when it goes in there and cures, it will still work effectively. You just don't want any large loose pieces or dirt in the hole itself.
That makes sense. We've had a number of questions come in, different variations of what techniques do you suggest to ensure that the thread locker is delivered in the correct amount to the joint?
Yeah, actually, there's some variability to that question in terms of if you have a small bolt, typically anything 3/8 and under, we say typically 1 drop is more than adequate. With larger bolts up to maybe 5/8, you might put up to 3 or 4 drops. 1 inch, you might have to put like 6 or 8 drops. What you really want to do is just put a drop on, considering if it's a smaller size. When you put the nut on and run around, you'll typically find that it spreads itself out. So again, it's very robust. It's not like you have to perfectly cover it. The idea is more you just put it on at a spot near where the bolt's going to be, where the nut will sit on the bolt at the final position. And from there on, when you spin it together, it spreads out and applies automatically.
All right. How many times can you remove the fastener before you have to reapply thread locker on, say, a 1/4 inch bolt?
Our thread lockers are designed that they're single use, which means every time they come apart, you would have to reapply them. The product in itself is a material that's a liquid chemical. When you put it in, it solidifies to a solid. Once you take it apart, you've broken the bond, so it cannot be reused in that sense. It has to be reapplied because it's not gum in the joint. It's actually a hard cured thermoplastic material, so it will not self-heal once you've taken it apart.
I see. Can you comment a little bit on the effectiveness of a liquid thread locker versus a chemical patch?
Yeah, the chemical patch, it can mean different things to different people, so it's more challenging to actually address that. But a chemical patch typically is where you're putting a chunk of nylon typically on the bolt side, and then you spin a nut on. It really is just to act as a bit of a thread jammer, and it'll have some effectiveness at keeping the bolt from completely falling off, which is good for certain parts, but it doesn't actually stop the bolt from rotating. And as soon as it rotates, even like 1/8 of a turn, you've probably lost 3/4 of your initial clamp load. So their effectiveness isn't high. They're often used just because people are concerned they don't want the nut to fall on the floor. So it depends on what your measure of success is.
All right. One of the viewers says that their company, they build products in here and then in Europe, Asia, and South America. So how would they specify a chemical thread locker to be sure the proper material is used for production, in different parts of the world?
Yeah, if you have a production application, we have field specialists that we recommend taking a look at the application. But because it is a global industry these days, we've really taken pains to actually standardize our line on a worldwide basis, and there are a number of grades that are available on a worldwide basis. 20 years ago, that wasn't very much of a concern, whereas today, it's very common that it's spec'd in, for example, the USA, it's built in Brazil, and you want to make sure you get the correct material. But it's best to work with one of our specialists on it just to double check it.
All right, we've had a few questions, and let's make this the last one because we're running out of time. But we've had a few questions about temperatures. Someone asked, are there product concerns at low temperatures, say minus 55 degrees Celsius? Another person wrote in that they have a product in a 120 degree Fahrenheit aqueous solution. Any comments on temperature ranges or issues?
Yeah, typically the high temperature is more of a concern for our product because at some point it'll carbonize, which is sort of like throwing a steak on a hot grill and leaving it to cook too long. But that takes about 500 to 600 degrees Fahrenheit, much like if you want to burn a steak on your barbecue. The cold temperature isn't as much of an issue for our products because it becomes a little more rigid, but fundamentally it doesn't damage the performance of the material.
All right, great. That is all the time that we have questions for today. Thank you again so much to Doug and to Rob. For all the questions that we did not have time for, the Henkel representatives will be answering them to you individually via email. And beyond that, if you think of questions down the road that you haven't had time to ask today, you're welcome to email those to me at Pheney, P-H-E-N-E-Y, at WTWHmedia.com, and I'll be happy to pass them along. Thank you. Oh, and one other quick thing. I know we've had questions. You will get a copy of the presentation. It will be emailed to everyone in the coming days. Thank you, everyone, for attending the webinar from Design World and Henkel, and have a great rest of your day. Goodbye.
Thank you.